This lecture is on a specific type of power series called a geometric power series. And we start off based on a formula that we learned probably back in Algebra 2. And we have this idea that we have an infinite series, geometric, n equals 0 to infinity of a times r to the nth power. So r is your common ratio, and a would be your first term. That is, if you plug in 0 for n, you get a times r to the 0, so a is your first term. And the sum of this infinite series could be derived to be a over 1 minus r. And this, of course, is assuming it converges. That is, the absolute value of r, your common ratio is less than 1, so between -1 and 1. But now we're going to kind of go in the opposite direction. If you have an expression which looks like this, 1 over 1 minus x, then imagining that 1 is your first term and x is your common ratio, so to go in this left to right, you can go right to left, and you can write it in this form. Sigma then goes from 0 to infinity of 1 times x to the nth power, again, assuming that the absolute value of x is less than 1. And then if you go further on and you write this series out in its constituent terms, you get something that looks like this. So here's a power series that comes out of this rational expression. And so sometimes, though, we want to adjust these things slightly, and at other times we'll do more than just a slight adjustment. We'll differentiate them, integrate them in different ways to get several different types of approximations. But in general, we can start off with this procedure. We want to center it correctly, so we centered at x minus c. That's will be our center. We need to get 1 minus x minus c in the denominator in order to match it up with that formula of 1 minus r in the denominator, and then we simplify the numerator. Once we've got it in the right form, we can find what that first term is, the numerator, and find what the r is, and we can write it as a power series. So here's an example using that procedure. We have 3 over 4 minus x. We want to center it at -2. So first we've got to change this x to an x minus 2. Well, in order to do that, I write this as x plus 2, because x minus -2 is x plus 2, but that changes the 4 to a 6 because we have to have equivalence in our denominator. If you distribute the negative, you have -2, and of course 6 minus 2 is your 4. Now we need to get a 1 here instead of a 6. So we divide everything by 6. So 3 over 6, 6 over 6, x plus 2 over 6. We simplify, and we get to here, and now it's in our form of a over 1 minus r, where our a is 1/2, our first term is a half, and our common ratio is 1/6 times x plus 2. Note that a minus is part of the formula, so r is positive 1/6 times x plus 2, and then we can go ahead and actually write that in sigma notation in this form here as a geometric power series. So let's take a look at another handful of examples. We have the function f of x equals 4 over x plus 2. We want to find a power series centered at 0, and so we can first write it as 4 over 2 plus x. The x I'm going to change to, well, I've got to divide everything by 2. So there's a couple algebraic operations going on here. We divide everything by 2, 4 divided by 2, 2 divided by 2, x divided by 2, and I change the plus to a minus and negative. Now I can see that my a is 2, my r is negative x over 2. I put it into my formula, and I get this as my power series, which you can express in this expanded form if you'd like. Here's your interval of convergence. One thing to note is that because it's geometric, and your common ratio always has to be less than 1, the endpoints are never going to work for this, so there's no real reason to check your endpoints for a geometric power series. They're just showing us another way of getting this by using long division. Here we have f of x equals 1 over x. We want to center that at 1. So in order to do that, we have to write this x in the denominator as a 1 minus x. I have to have a 1 out here to fit my formula. So a is 1 and r is 1 minus x, or alternatively negative x minus 1. You plug it into your formula, which is again is sort of the reverse of what we would have done in Algebra 2 and in math analysis and learning infinite geometric sums. And then you have this as your series, in which you can expand in that manner. And here again is your interval of convergence, and of course it's open on both sides. Operations with power series, well, you can do scalar multiples, you can take them to powers, you can add them and subtract them. As far as adding and subtracting, just the point they're making here is that the intervals of convergence are only the intersection of the two of them. That is, if one of them diverges in a certain section, then of course if you add a divergent portion to a convergent portion, it will diverge. So the overall interval of convergence of multiple series is the intersection of their constituent intervals. So here is function 3x minus 1 over x squared minus 1. A little more complicated than you generally see. Using partial fraction decomposition, you can get it to these two fractions. We can get power series for each of those, and then you can go ahead and add those together to get this expression, which can be expanded in that manner. F of x equals ln x centered at 1. If we want to find a power series for this, of course, we can do this using Taylor coefficients, as we've tried early in the chapter. However, realizing that we now have a series for 1 over x, which is given here, and ln x is simply the integral of 1 over x, you can get the series for ln x by integrating this series. And so in integrating this series, negative 1 to the n is a constant multiple. We add 1 to the exponent and divide by it. That's just simple power rule, and we have a plus c, constant of integration. And in plugging in our value at 1, we can conclude that our constant of integration is 0, and that leads us to this series for ln x, and going about it using geometric power series. And this is a discussion of how we did it with Taylor polynomials, or a reference back to that. Another power series by integration is finding one for arctan. And so, noting that the derivative of arctan is 1 over 1 plus x squared, we can start with 1 over x, or sorry, 1 over 1 minus x, then we get to 1 over 1 plus x, which is this series, and then you substitute in an x squared wherever you see an x. So here's the series for 1 over 1 plus x squared, and then we integrate that series because the integral of 1 over 1 plus x squared is arctan. Once again, our constant of integration will drop out in this case, and so now we have a series for arctan, which you can expand. Now, noting that then arctan of pi over 4 is equal to 1, you can actually, or excuse me, arctan of 1 is equal to pi over 4, you can actually get an approximation for pi over 4, which would lead, of course, to an approximation for pi using this infinite series. It converges very slowly. It's not a very good way to go about it, but it does in fact work.